PLC until January 20, and I think we would be happy to talk with any of you of any research problem you might be interested to share with him. And Victor today is giving a presentation on micro data centers, cloudlets for mobile computing. Victor, to you the show.
Thank you, Giovanni. Bonjour. I am really happy to be here. I'm actually on a sabbatical from Microsoft, which is sort of a weird kind of a thing. How do you take a sabbatical from a company? But somehow I managed to do it. I guess I'm fairly burnt out. So it's really fun to be here. And Giovanni's my host, so thank you for hosting me. And yes, I would be really happy to talk to any one of you who are interested. I've been looking at the posters here, and seems quite a lot of interesting work going on, so that's very cool. So what I wanted to talk about today, this talk is, I think, fairly long, so pardon me if I skip a few portions of it as I go along, and I will read your faces as I'm giving the talk, and that'll give me some input as to what I should not do. So if I'm doing that, I'll adjust in real time. But there is some history behind this talk, and sort of an interesting history, and I want to give you that. So Microsoft often has this thing called Disruptive Technology Review. And we started doing this about 4 years ago when the Microsoft CEO, Steve Ballmer, at the time came under a lot of criticism for not picking up on the search and mobile in time. And Google basically came from nowhere and became such a giant. And similarly, with Android and mobile, Microsoft already had a lot of good products in the mobile space already when the Android thing happened. And so the question was, why did we not see this coming? So as a result, the board put a lot of pressure on the CEO and said, hey, you've got Microsoft Research. Their job is to think ahead. Why don't you ask them what are the new things that are happening, and then maybe perhaps that'll help. So 4 or 5 years ago, we instituted this thing called DTR. So every December, we get together with the CEO and all the executive vice presidents and the top tier of management, and essentially talk to them about things that can potentially disrupt Microsoft or things that we can do to disrupt the rest of the world, so that the product groups at least have the data in deciding what they want to invest in. All right, so that's sort of the history, some story. Now, as part of that, this last, not this one because I'm here, we just did a disruptive review, but the last year I gave a talk on something very simple. I gave a talk on latency, okay? And my thing was that, look, we're spending, in fact, the IT industry is spending billions of dollars on cloud computing, right? These mega data centers are very, very expensive. And we're also, most companies are moving in the direction of trying to build this hardware too. So, Microsoft acquired Nokia, we build hardware, we build Xboxes, we build Surface computers, phones, bands, lots of hardware is being built. So think of it as clients. So we have the clients and we have the cloud, but the middle is kind of still a question mark, right? That's the internet and all the other things. And so large companies cannot just allow, when you have billions of dollars at stake, to just have question marks where we are sort of hostage to somebody else. So the talk revolved around latency. Now, in order to build the talk, I pushed this concept of micro data centers, which I had actually written a paper on with Satya in 2009 called Cloudlets. So this is the background with which I'm going to present this. Obviously, for obvious reasons, I'm not going to present every detail of what I presented there, because there's some competitive information in there. But I wanted to share with you the thesis of this talk, because I certainly believe that in the next 5 to 10 years, the cloud is not going to look like the way it is now, and it's going to be a lot different. And so as I give the talk, feel free to interrupt me, please. Ask any question you want. It's much more interesting and interactive, even for everybody else, if there's a lively conversation as opposed to just a lecture type of course, which All right, so just a preliminary. I'm going to focus primarily on mobile computing, okay? But this extends well beyond mobile computing. This is a nice graph that I borrowed from Satya. The point of this is that that the way our lives are evolving, we're doing a lot more in a lot less time, right? Certainly true. And the issue is that when we do a lot more with things like phones and bands and things, we're constantly context switching, which means we need information instantly. Now, the question of instant information instantly, there's a lot of work in computer science and EE, which actually allows us to do that. There's been lots of progress in vision algorithms. I mean, Microsoft, for example, yesterday released a preview of a real-time translator over Skype. So you talk in English, and immediately you hear in Spanish, and vice versa. And if you think about it, it requires machine learning. It requires obviously image translation services. And these things we can do, but they require a lot of resources. Okay, so resources that are not necessarily available on our phone. So the challenge then is that how do we get to the point where we can bring all this innovation that we have been doing in different fields, vision, for example, on our phones, on our devices that we're carrying all around, right? So that's sort of the big thing for us. So here's some very rudimentary, simple examples here. This is about 3 years old video now, but it still is decent enough that I show it. What is happening here is that the individual is wearing a camera and is walking around, and you can't see this very well, but there's a red spot here, and so it's doing indoor localization through vision. Okay, so it's actually processing the pictures it's seeing fast enough to be able to show, for example, where that individual is in the corridor. Okay, which means we do have the ability to do these sort of things. In vision, for example, the big things are who are you looking at, or what, where are you, and then what. So this is also a slightly old video, and again, this at the time sort of shows the state of art where you're picking up objects and sort of seeing what the objects are. But realize this is all happening in real time. It requires, sir. Hi, how are you, sir? It requires a lot of processing, which we can't do today. Okay, so we have a project called Project Glimpse. You can actually, if you go to my website or somewhere in there, there's a video for this. The idea where the guy wears a camera, and instead of doing real-time processing, we do quasi-real-time processing, which means as the individual is walking around, the video is being taken and it's being processed, and then you can look at the video of all the things you have been seeing right there at that instant. Now, there are two distinctions between this and what you see in, for example, Google Glass and things. In the Google Glass scenario, you have you sort of look at it while you're doing it, and I think that to me doesn't sit well with me personally. It's just a matter of choice. So what I would rather have is the camera is embedded. In this case, he's wearing it in the ear, but you might know that, for example, in London, police officers now have cameras stitched on their vests. So you can imagine cameras sitting, which are, but then you use the screen of your smartphone to look at whatever you want to look at. So in this particular case, you look at things that the individual has missed but happened just a few seconds ago. Now, this gives the computer a little bit of time to go and process the data and bring it back to you. And so, you can do the sort of same thing. You're looking at some grocery items, and it tells you all the calorie counts and things. So this is a Project Glimpse. There's a few papers around it.
Where is the processing taking place?
It's taking place in the cloud. I'm going to get into that a little deep, not on the phone. Now, remember I started this talk with the latency thing. So one of the things people always ask, and the execs always asked, was, can you quantify there's money involved here? And that's really hard to do. But I looked around a little bit and picked up some of these quotes, and as you read them, you will notice that there's actually real money involved. There has been lots of studies which say that if you don't bring the data right away, then you're going to lose customers. In fact, if somebody else brings the data, that gives you the data faster. Then, to give you a sense of this, is that relevancy algorithms in search, right? The way they sort of work is You issue a query, the query responds threads, the threads start operating, a certain time comes, there's a cutoff, and immediately the page gets populated, and that's what you get. Now, any amount of milliseconds that you spend in the network, from the time you issue the query to the time it hits the compute servers, that's wasted time. If you can cut that out and you can use the same time to do more processing, so do more brute force, you're going to get better results. And if you get better results, your thing would be a lot better. So it's not like, for example, Google's relevancy algorithms are better than Bing's relevancy algorithms. They're not. They're actually, both teams have got amazing individuals, researchers working on it. And head-to-head, they're equivalent or one is better. It really ends up being, believe it or not, the network. The faster speed networks allow more processing time. More processing time leads to better results. So there's real money in all of this stuff. OK, enough said. So now let's get into a little bit of technical thing and sort of architectural thing. So let's make it very simple. What does latency come from? And by the way, I jumped into latency when I was talking about all the compute resources. I did mention that the processing is happening in the cloud, and there's latency between the device and the cloud, and we're going to try to handle that a little bit. So simply, you do something in the client, you send it, right? Take some time, send it in the data center, run some stuff there, comes back, and then you have some client processing. Now, in Microsoft, and generally in the academic forums, in some of the top conferences that I track and I go to and all that stuff, there's been a lot of focus inside the data centers. And understandably, and so we have done some tremendous work there. For example, we went from networks being the bottleneck to creating full bisection bandwidth networks, right? This is completely architecturally different from the way the networks were. We have gone down the path of creating software load balancers, which make sure that these networks are handled really well. We've got the inter-DC data center bandwidth utilizations used to be about 40-45%. Now it runs at 90-96% or 95-96%. So we have done some amazing work in these areas where we're getting rid of it. But we have not done that much in the internet. And what I mean by that is not to take away from all the different research that was going on the internet a long time back. When I started hiring heavily into my group in 2005, every student that I viewed was doing stuff in the internet. But that didn't work, didn't go too many places, and primarily because it was really hard to fix the internet. But I'm going to show you how I think it'll get fixed as we move forward. OK, so so this is just a simple experiment that I did from my office. I just, over Wi-Fi, I did a trace route to some Google thing, and I got this many hops. I did the same thing over 3G network at the time, and I got these many hops. And you can, this is quite repeatable. You see different number of hops changes. And then you say, but look, this is terrible. I mean, the latency here is terrible. The number of hops are terrible. It's just bad networking when you're taking this number of hops there, right? So what is going on underneath? Yes?
But if you look at the bad latency starts at hop number 2. And it starts right away. Yeah. And 3G.
True. True. We'll deal with that too. That's true. I will. If I don't address that, ask me again. So again, sort of demystifying the internet a little bit. All of you know this, but really what it is you've got clients, you've got data centers. It's running through a whole bunch of ISPs, like the BGP protocols running, negotiations happening, packets go this way or that way, depending on whatever happens. And it's huge, right? That's your internet. So how are you going to tame this beast? Now, add to that the complexity of wireless networks. So this is sort of a picture from the 3G thing. So this is one little part of it. And then you see how everything is interconnected. And of course, there will be latency. So there have been papers in 2010. Here's one paper, 2030. This talked about what was sort of the medium latency. So 450 milliseconds, 350 milliseconds. This is huge numbers. I'll show you how huge they are in a few seconds. And then if somebody says, hey, LTE has solved the problem, not really. LTE is a medium. Rule of thumb is about 70 milliseconds, but the jitter is pretty high. This is from 2013. And I believe, in fact, every time I have a software running here, you can actually download it too if you have Windows, called a network speed app, and you can try it. I try it here every once in a while. It's really bad. It's not even this number, so this is very optimistic. Now, when somebody says, especially when you're talking to execs and you talk about milliseconds and they don't quite get what milliseconds is, then you sort of say, well, actually, it's really bad because our protocols are kind of busted too, right? This is the TCP protocol and add to that TLS. And so if you sort of say, what does it mean? What does 50 millisecond latency mean? Really, it means about 530 millisecond latency. And that becomes pretty significant as you do more and more transactions. So this is just a picture to demonstrate that the protocols will add tremendous amount of latency to what you see. And there's the thing that I mentioned. Feel free to download, and I'm sure there are others in other platforms as well. And this will so none of what I'm saying is incorrect, because as you try it on real-world networks, you will see what the latencies are, and you'll be surprised. All right, so the ground truth is high latency and jitter degrade services, and they can become unusable. So the kinds of things that I was showing you earlier, the Glimpse, I had the Glimpse project, or any visual analytics, or anything that you want to do fast is going to get affected by the latency. And to the point that it's actually not usable, right? If you're doing something real time, you can't bring any of that computer science thing into use. Better quality internet path will give you less latency. We sort of saw that anecdotally. And this this bullet is really important whenever you give an internal talk, right? All right, so then we'll say, let's take on latency. All right, so then, again, simplify. It's whenever things are, at least for me, whenever things are hugely complicated, I just kind of give up and just look at it from a very, very higher. So I look at cloud as a world, and I look at sort of the internet that connects. I look at peering points, right, that you connect. And then you have some ISP networks, and then the consumer networks and the seller. Now, it turns out, this was actually a revelation for me. It happened several years ago, but I'll share with you. I don't know if you know this or not. So we know in the IT industry, we sort of think this is where we are spending a lot of money. Turns out that's true. And we spend, as I already mentioned, billions of dollars here. We do it. Google does it. Amazon does it. Facebook probably does it. Apple is doing it. Anyway, and we also spend a lot of money in trying to fix this. Turns out we actually own a whole lot of fiber too. Okay, we own, Microsoft owns more than 25,000 kilometers of fiber right in the US. Not a joke, that's a lot. And we continue to acquire that. And we take it to the peering points, because we actually have great products which will say, hey, come to the peering point, we'll take it from there and we'll bring it back, right? And then, of course, then there are these regular ISP networks as well, including the cell networks and things that happen. Now, so we've been focusing here, right? And now you would start to hopefully see a series of papers come out of at least my lab, and potentially from others too, where we start to fix this. And the epiphany for us has been what happened here can happen here, which is in here, we decided, hey, we owned everything. We owned the networks, we owned the clients, we owned the servers, we owned everything. Why the heck did we have to fall hostage to anybody doing a network? So here we are realizing the same things. If we put a bunch of servers here, we already own the servers, we buy whatever equipment we buy, we can fix this stuff. And so we are going to. Now, but really, I'm more worried about this area, because this is not easy to fix. So going back, so how do you reduce latency? Well, the thesis is that the moment the packet leaves the client, you want control of it. And the way you're going to do the control is you're going to bring the cloud closer to the client. Okay? So then you say, let's build lots of data centers around the world. And in fact, that's what's happening. Everybody's doing that. They build these mega data centers for various reasons, not just latency, but there are all these rules that have to be followed, where the data should reside, not reside, things like that. And so you build these. I just put these things randomly. They're not supposed to be accurate, but these are trade secrets and things, and I don't. And so a lot of data centers got put. But is this enough, right? And the answer is no. It's very capital intensive. These data centers house something like 200,000 servers, 100,000 servers. This is very, very expensive. And there's a churn of equipment that has to happen. So very expensive. You can't do it. So the other smarter approach will be that, hey, let's build these thing called micro data centers and build thousands of these and put them all over the internet. And let's put them as close to the users as possible. Right? Now, of course, there's science to where you're going to put them, right? And we can go into that. We as researchers, we can sort of, those are the kinds of problems we're good at, and we can go after that. But really, the idea being that once you have these micro data centers, then when traffic comes, you're going to route it to the closest micro data center. That data center, by the way, in the academic community, I call it Cloudlet. but that data center will try to serve you, and if it can't serve you, then it'll have a tunnel or maybe a thing to the larger data center and push the pipe there. Now, the network between the micro data center and your cloud is the network that you can actually focus on fixing. So now you've taken a large problem and sort of reduced the scope of it, and then you can go after that problem. Okay? So for example, here's a rack of servers that can be a data center. It can be 40, right now there's like 20 to 40 servers. It can be smaller than that, and it's not that expensive to put. Now, so assuming you buy into, yes?
I'm just not sure, why is it less costly? Why is it less capital intensive or less costly to operate? It seems to me the other way around, my intuition would be because it's easier for a fixed number of servers to manage them all in one place, rather than to have the management overhead of many different locations.
Yeah. So so that's the classical cloud thing, which is that, hey, put it all together, and when you distribute it, what'll happen? So I'm going to just, you're asking good questions, but I have to defer them because if I tell you, then I'll be giving you some punchlines away, which will kind of take away from the fun part of the talk. But if I don't answer, please do bring me back and ask me, because I do want to answer them. Yes?
Maybe I want to follow that up.
Yeah.
See, because I worked at Bell Labs in the 1980s.
Yeah.
And when this divestiture was going on, they had the same idea of POPs.
Yeah.
POPs. I was POPs planning. So you put all these guys to take traffic locally away.
Yeah.
It didn't work.
Why not?
So why are we revisiting these ideas unless we have something to back up that we've got something more?
Yeah, we have something more. I mean, so pardon me for saying this, okay? Pardon me for saying this, because I've also gotten to an age where I also, when I listen to talks, and I say, oh man, I did this a while ago, what the hell are they repeating it? But the point is, after reflecting about all these things, I think many things have changed. I don't know when, you were talking about 80s, between now and then, and there's lots of reasons to do what we're doing. So let me again try to make my case, and if I haven't made it, we will revisit. Okay, so these are good things, okay, so let me get into what micro DCs can do that POPs may not have done. So I'll start by saying that you're kind of sort of using them already, okay? So when you do YouTube, I saw some posters in YouTube here, you're actually using something called a micro DC. It's not called micro DC because you're using caching, right? The way YouTube kind of sort of works is, it's a classic CDN. They would, Google or company would sort of say to the ISP, hey, we can save you a tremendous amount of upstream bandwidth, which they have to pay to the ISPs. If you take this server rack with a lot of memory, we're going to cache all the YouTube video here. So your customers are going to hit this, and we don't have to go to the cloud. You get the latency benefit, and you don't have to pay. So it's a win-win for all. And so what Google gets in return is they get rack space and they get power, right? Which is what they really need. So plug-in space, power and play. So caches are being used already, and there's a huge market for it. And there's a huge number of companies that do that. So now, one of the things that the caches do is they also provide proxy services now. So you can do split TCP. And for those of you who are in hardcore networking, you understand that you don't want to wait to take the full round trip before realizing packets have fallen, bad things have happened. If you can sort of isolate it from between you and the proxy and then have a persistent connection from the proxy back to the cloud, your performance improves. And there is actually data for that. For example, on an average, 30 millisecond can be improved, and 30 millisecond actually contributes a lot to this kind of stuff I've talked about in terms of relevancy things. And a lot of people are already doing this. So MDC is actually, the way sort of I think of them is go beyond that. They're not just purely caching and proxying, they're actually going to be doing computations. Now let me now go into some examples of the benefits of this. I'm going to go with something that is near and dear to everybody who uses a mobile phone, and that is battery life, okay? And in order to do that, I'm going to actually I'll tell you a story. So the way smartphones work today, and this is true pretty much everywhere in the world. Sorry, I don't know if you can see. I don't know what to do. I'm actually getting pressure. I don't know where to stand, because everywhere I stand, I'm going to so I'm going to alternate. Anyway, so the way it works is these numbers are real numbers. This is 1.6 watts. This is 0.0 watt. And so when you have data, the data gets transmitted. The radio is up. It stays up for a little bit, okay, and then it stays up and then finally falls down, right? You might ask the question, what the heck's going on here? There's no data to transmit. You're actually using 1 watt. Why are you doing that? Okay, So this is true. So why are we like this today? Well, it turns out that, I don't know if you remember, but approximately 5 years ago when iPhone was introduced, there were these articles in the New York Times. Does anybody remember anything? Like, there was this, you remember that in New York City, iPhone was introduced and it brought down the entire network. Literally did. Like, it just stopped working. And so these are from that time. For example, 2009, 2009, so about 5 years ago. So what was going on? Well, so what was going on was iPhone, like IT guys who know will say, as you might have thought, and as I sort of hinted at, you have some data, you transmit it, you're done, you bring the radio down, you sleep. When the data comes, you wake up. Well, it kind of screws things up because when the cell phone network was created, they came from the telephone sector where they very heavily believe in circuit switching. So what happens is when you turn something on, a signal gets sent across the whole network, and so all the resources get built up. The moment you bring the radio down, a signal gets sent, and all the resources bring down. So now, web traffic is very bursty. Emails are bursty traffic. And so if you're doing this, you're generating so many signals in just one session, and all that the network is doing is bring things up and down. We're setting up resources, bringing out resources. And it's not built to handle that kind of a frequency. So everything just died, right? It didn't work. So the MOs quickly realized this is a problem. We can't allow this to happen. So then they said, okay, fine, you can't do this. We're going to mandate this, that you can bring it down to this. The lowest level is 1 watt for you to think that for the telco network to think that it's still up. Your thing is up. And then you've got to wait a certain amount of time. It turns out they wanted you to wait 9 seconds. They decided, because their thinking was that within 9 seconds, if you were doing something, you would continue to doing this. So it's sort of like managing the hysteresis, and if not, you can bring the network down. So that's what they started to do. Well, that's really not good, because you are going to spend lots of energy. Okay, so for example, LTE chip active for about 10 seconds extra wait time. So one thought is that if you have a micro DC right at the edge, okay, near close to the base stations and things like that, you can actually behave like the micro DC can actually behave like a proxy. So the radio can shut down, but the proxy holds that signal for the n number of seconds, and then releases that signal to the cell guy to decide that now you can bring the network down because it's not active. So now you've saved a tremendous amount of energy on the client side, and you've not hurt the proxy type. So if you want to do some quick math, energy saving per transfer is 1.6 watts times speed up, because I'll show you that actually MDCs will speed things up too. So that's the speed up, plus 1 watt times 9 seconds that it's waiting. So you're saving 10.6 joules per transaction. And so now if you think about like just a regular battery, a 1500 milliamp, this is when I had done the talk, the battery powers have become better. That's 26% saving. That's huge, okay? If you sort of want to do this more, and if you think about how many transactions you do in actually a second, well, not you, your system is doing, there are quite a few. And so if you draw on the horizontal axis, draw the number of transactions, on the vertical axis, draw the battery lifetime, you start to save significant amount of battery life, right? 75%. And this is across any battery type, any mobile device, anywhere, so long as you're on the cell network. And again, if you don't appreciate this, just think about the following graph, which is then the time that the CPU has increased by about a factor of 250, we have increased just 2 or 3 times in terms of batteries. There's nothing magical going to happen in the battery. You have to find these solutions to do that. So this is a significant improvement, because now you've got something at the edge which is proxying for you. Okay, so that's one case for that. Any questions on this?
Even with Tesla's research on batteries.
Yeah, sorry, I was like, yeah.
No, you were talking about this with respect to battery savings. So I was just thinking about what Tesla is doing for energy savings, and the fact that they're working on having batteries that can store a huge amount of energy.
Yeah.
So how does this going to affect?
Well, so I'm fairly skeptical about how much. I've seen all the predictions of, and I've seen some of the technologies of how much batteries can improve. And I don't believe they can improve at the same speed at which we are trying to do the processing. So, I mean, one way to think about it, the more energy you put in a small compact factor, small device, you're really making a bomb at the end of it. And there's only a limit to how much you're going to do that. So, regardless, so to be more charitable, let me answer the following, answer it this way. Regardless of how much battery you improve, this kind of saving is still going to be helpful. Right? We have I have a researcher in my group who has given a talk and got lots of public for a press for it. He says he's been working on things which are give you a 7-day battery lifetime. So you buy a smartphone and you don't have to charge it for a whole week. That's a game changer, right? If you have that, that's going to be a big thing. So anything we can do in this space is really helpful. So sort of generically, yes.
There are two things, right? One is how much energy you can store, and the other is how long it takes to charge your battery.
Right.
Because if you can reduce this time by a factor of 100, then you
Yeah.
have, right?
Right.
I've been reading that the enhancements in this area are huge. What do you think about it?
So there is a fundamental trade-off when you get into battery technology, which is the batteries that charge fast will discharge very fast as well. It's not like they will charge fast and you can sustain them for very long. And so similarly with the ones and that's very fundamental to the chemistry and the way things work. And so, yes, it's true that progress is going to be made. Like you will have these surfaces where you can just put the phone and it'll just charge it up, or that'll happen. But I mean, I think that this kind of improvement should be done regardless of all that stuff. This is just it's going to get worse and worse for all of us. It's going to get worse and worse for any variable things that you get. All right, keep going. So the other thing I want to talk really quickly about is offloading. Okay, so one of the things I didn't say, but it was sort of implied there, was that there's not enough processing here. So what you want to do is you want to offload some of the remote execution, and there have been lots of papers on this subject, so I'm not going to belabor this point too much, but I do want to cover it. Now, as researchers, you think, okay, fine, I believe in offloading, and I'm going to offload some of the computation to a server with stronger, but the question is, what should I offload, right? And should I decide that statically or dynamically, correct? And then another question that most researchers don't ask, but when you're in industry, you actually have to ask is that, how do you do it so that it's really easy for somebody to program against it? That's really important, because PhDs are not the ones who are going to be programming these devices. So you are free to look at a lot of this work that has gone on. There's a lot of literature. We had this paper called MAUI in Mobicys. USC has an Odessa. Intel has this thing. And so the way these guys, all of them work, for example, they will offload at different resolutions. So for example, MAUI will offload at the method resolution. Clone Cloud is essentially basically creates a virtual machine, really, and tasks, etc. So just to give you again flavor of how this all works, let me walk you through something fairly simple. So most of these inherently work the way that I'm explaining, but I take MAUI as an example because that's what we built that I was personally involved with. So you have this notion of profiler. What the profiler does is it takes the call graph. So if you program in software, you have a call graph of which method calls which method, etc. Right? It takes sort of the execution. This is all kind of done offline. It takes the execution time of each of these call graph, which you can do as you compile it and run it. You can actually figure these things out. The size of the state, because what you're going to move is you're going to move with method plus the state with it, the number of CPU cycles, etc. And what you dynamically look at is what is the latency, because there is an inherent trade-off, right, which I'm going to tell you about in a few seconds. That is between communications and computations. And you have to take all that into account. So latency, bandwidth has to be taken into account, and that is all dynamic, because you don't know which kind of networks you're connected to, and some hints as well. Now what the profiler does is it takes all this as input and then generates this kind of a graph, which says method A calls method B, which calls C or D, right? But then it'll augment it by these numbers. So it says method A, for example, will take about 45 millijoules. And the total state transfer from A to B is about 12 kilobytes, or 10 kilobytes in this case. And that should take about 30 milliseconds given what you have. So magically, these things appear, but not really magically. There's actually some intellectual horsepower that goes in. And I'm going to show you an equation. That's not to impress you, but that's just to show you that there's some science behind all this stuff. And so once the profiler has generated this, what is happening is there is a decision logic. The decision logic is going to decide whether it makes sense to transfer it and compute it, offload it, or compute it right where you are. And the way, sort of, if you look at the equation, what this equation is saying is this component says, what is the energy saved if I offload it and let somebody offload it there? Subtract that with the cost that the energy used to offload it, right? That's because you're wasting the energy. In such a way that the total execution time plus the time to offload is minimized. So essentially, the point is that you've actually created a program, linear program that you can execute now, fill in the parameters, execute, and the answer will show up, which will say whether you should offload it and shouldn't offload it. And I'll show you an example of where these things and how these things work. So look at this graph. It says the execution time, duration, and these are the different types. And so the way to read this is that this bar shows if you're doing a face recognition task only on the smartphone, how long will it take? So it takes about that much time. This is what happens when you offload it, but then this is with all the different latencies to the cloud. Okay, so as you can see, as the latencies go up, of course, the execution time, the total time goes up, but you can sort of like, it's doing what you expect it to do. And now if you look at so this is about speed, how fast things can be done. So now if you're doing a real-time task and if you offloaded it, you can get the answer back quickly as opposed to not. This graph shows you the energy. Now, in this case, it's a more interesting graph than that, and for the following reason. That, again, the legend is the same. This is only in smartphone you use that much energy, and this is when you offload it, when it's running. Notice that in this case, which amounts to a latency of about 220 milliseconds at the time, this is taking more energy, right? The system actually stopped. It did not allow us to do that, and we had to hard code in to sort of show that, which means it was doing the right thing, which is it was not going to offload when the RTT was long enough for it not to make any sense to it. And so anyway, so I just wanted to give you a point that there is a lot of work that has shown again and again that if you take these processes and offload most of it, you are going to benefit. And then of course there's underneath you have, and I'm not saying this is the best way to do it, people have different ways of doing it, but this is what you can do from MDCs. Now I'm going to show you an example of when it actually does, and you will see something interesting here, and I'll point you what it is. Whoops. Sorry, but before I start this, I'm going to set it up. So what is happening is, so there's this intern of mine who had asked, she was standing with her smartphone and taking a picture of her friends walking by. And the idea was that you need to recognize the face of each of them on the smartphone and tell who it is, right? So that's what's happening. So this is what she originally captured. So it'll show you original capture. Then it'll show you what happens when the latency is a certain amount, and then we increase the latency, and it shows what happens then. Okay, and even you're offloading this whole thing. Okay, so it's a very short video. So these are like 7 people walking, just friends. So now you have about 5 millisecond latency to the server, and then you start to see that it recognizes these individuals, right? Now we're going to increase the latency to about 75 to 85, which is the LTE latency approximately. And then you see this. Now, what you didn't see, you saw some faces being recognized, but what you didn't see is that in the first case, all 7 people were recognized. In the second case, only 4 people were recognized. Now, that's pretty serious, right? So if somebody was to build a system where you had less latency and all that were recognized, you would buy their system over this system. And that clearly shows that the quality impacts. Now, what I want to show you is actually a really interesting graph to me. Any image analysis work can be broken up into these components. So you have this notion of, so I'll take the face recognition, but you can take object recognition or anything. You have the detection component, then you have some alignment, then you do some extraction features, and then you do pattern recognition. Okay, so that's how kind of all vision algorithms work. Now, the graph that is interesting to me is that this is the in this particular case, here's the time you have for computations. Here's the accuracy, and so n is the number of features you can extract. Okay, so let's say if you had some, like for example, this much time for computation, you could extract only 3096 features and you would get about 72, 73% accuracy. But if you had something like 500, you might be able to extract more number of features and get more accuracy, right? Seems kind of sort of logical. But the beauty is that this is actually true for not just object recognition and image recognition, it's actually true for speech, and it's actually true for search. The exact same thing. They work very, very similarly. And these are the two big things that we do today, right? So the more time you have, and that was my point that I made earlier, which is you can do better and you can get much better accuracy. So latency will kill quite seriously. Now, just to speed things up, let's see. Here's another example I'm going to give without going too much deep into it. The idea here is that many times what happens is, I mean, here I noticed that you guys are actually very lucky because you seem to pay very little for a huge amount of bandwidth. But a large part of the world, you're paying tremendous amount of money for the bandwidth. In fact, I'm paying $60 for 300 megabytes, and I'm always watching what the heck. It's like eating up, because every time I do any GPS and do mapping, I eat up 30 megabytes or whatever. So bandwidth is kind of expensive in many parts of the world. So what happens is most application writers don't write applications with that in mind. So there's a weather app as an example. What it does is when you look at the weather, it'll bring all kinds of fancy pictures and things like that, which consume your bandwidth. But really what you want is a number. You don't want all those pictures involved, right? And then not only that, because the app is such, if you sort of go to the next page, it brings all that data as well in there without you may never even use it. So it's consumed all your bandwidth. That's a bad idea. In fact, this picture sort of shows that some apps are worse than the others. So for example, MSN apps, which is Microsoft's app, is kind of really bad because hopefully they saw this and they've improved it, because this is sort of an old data, but we call it the way it is. I mean, what can we tell you? So the weather app is kind of sort of bad. So red shows what you use, and blue shows what you could have saved if you hadn't brought in all the pages and things. So now with an MDC, the idea is that, hey, so you don't want to change the app, but what you want to do is when the query is sent, you bring in everything, but you store it at the MDC or the Cloudlet, and then you only pass it if the user goes. And I'm going to show you how it looks. So first example is when you you don't bring the data, so you try to do the saving. So the app runs, and it doesn't bring the bandwidth, and so every time you go to the next page, then it pulls it in. And then this one shows that when the MDCs work, and you can see the difference between the two. Is it working? What did I do? Yeah. So I don't know if yes. So now see how long it takes the time. Took some time for the map to come. It actually gets pretty aggravating as you run through it. Now I'm going to run this one and watch. And by the way, no data has been brought to the client, but watch the impact of an MDC. So here's the weather channel. It brings it in. Now it's going to go to the next page, and boom, it's there. It actually wasn't there when he brought it in. It was there by the MDC. So he had saved the bandwidth, but he brought it in. So again, this shows that by cutting down, by bringing the cloud close by, you can do these sort of things. So now, really quickly, if you have these cloudlets, you can create an overlay network on top of it. So you can bypass some of the ISP's network. I'm not going to go through that, but I'm going to tell you. So there are many things you can do. I need to wrap things up. Many things you can do if you have MDCs. So caching and static component and SSL termination is something we already do. Bandwidth saving with compression we already do. Procrastination is an example that I showed you. Service and internet monitoring is a really important component of anybody who is managing these clouds. And so you've got all these vantage points. In fact, there are companies which have made done their business by deploying these things on the internet. But you can do them. Reliable connectivity through overlay networking. All the work that was done in the past, you can actually bring to bear. App streaming, this is also a big trend these days. For example, if you want to run, I have a video, I'll see if I get the time to show it to you, but you can actually see that when you run the games in the cloud, so one of the ideas is if you run Xbox games on the cloud and you can play these massively amazing graphics on your little device, if you do it fast enough, you can, you've got a winner there. But they can only work if the latency is very low, right? So now with the cloudlets right at the edge, you can actually do a lot of that. I can show you that thing. And so then there's the other thing that people are interested in, the denial of service attack. So imagine a cloud with the tentacles where all these cloudlets are sitting, or MDCs are sitting, and they're looking at the traffic, and you can cut that off whenever you see the denial of service attacks happen, as opposed to them all coming into the data centers and then you're doing other things to it. So a bunch of things you can do. Now let's talk a little quickly about deployment. Now I already sort of talked about the peering points, which is where we deploy MDCs. But there, so that's sort of a brain dead thing. You kind of just do it. But there are more interesting ways to do it. And so for example, let's consider a wireless network. Wireless networks here and everywhere in the world are basically dumb access points with smart wireless switches. That's how they work. And so imagine bringing a rack of servers and connecting it right next to the wireless edge, wireless switch. And you can imagine companies being formed which will not only now provide you with switch, but will provide you computational resources at that switch. And that's your MDC. And so there's a bunch of companies that can do that. Now, yeah, so here's the thing I wanted to show you, I guess, the gaming video. So this is what happens with regular motion or 5 millisecond latency. So he's an expert gamer. He's clicking on it, and you're seeing him punching, right? With 30 milliseconds, you can start to see some difference. With 80 milliseconds, this is not acceptable. You can't play the game. If you're a good gamer, you can't play the game. I'll show you a couple of other examples. So he's turning again with 5 millisecond latency. So here what we have done is we've got the cloudlet sitting right at the wireless edge server, and it's streaming the game to the device. Not a smartphone, but you can imagine this to be a smartphone with different latencies, and you can see how bad. So this is the best one. So here he's shooting, and at 5 milliseconds he's rocking, right? I think this game is called Zoom or something. Zoom something. I wish I was a gamer. So he's able to shoot everybody at 5 millisecond latency, right? Because it's very good. Now we have 30 milliseconds latency, and now he's getting shot quite a bit. I don't know if you're noticing, but he's shooting because he's still very good. But see, he's getting hit. He wasn't getting hit before. So now what we're going to do is we're going to have him play this game, but put it in the cloud with about 80 millisecond latency. It's actually quite dramatic with the sound. I don't know why I have no sound. All right, here we go. We can shoot. Now the poor guy is getting hit again and again. He's not able to react, but the guy's right in front of him, as you can watch. He kills this guy, but he actually dies. Basically, that's what happened. So the guy kills him. So again, the point is, if you want to do streaming, and if you want to run these massively compute-intensive, graphic-intensive things in the cloud, you can't do them without this thing. So I told you about the thing about Wi-Fi. And so in the cell domain, yeah, you asked me the question about LTE. So here's my answer to that, part of the answer to that. So I don't know if you've been sort of following. So in a cell network, if you deploy, you're not going to get that much advantage. I mean, there's some advantage because the cell network itself is going to do it. So what is going on there is you have this whole idea of small cells. And if you've been following small cell development, which is actually taken off quite a bit in the US, and I suspect it'll have, is all about improving capacity. And there's a whole talk to be given if you, but they're doing. But small cells are not so different from Wi-Fi networks. And so we have a small cell deployed in our lab, and you see that latency between the phone and the small cell is about 3 milliseconds. So this is part of the cellular network, but different from it, because now you're going to have much more capacity. And so as opposed to, so it's shaving off, in this case we actually had very good connectivity, but it shaves off 30 milliseconds. And so here's some numbers too, just to sort of whet your appetite. So download throughput is fairly reasonable. I mean, this is I guess LTE, and then here you get up to 120 megabits per second, and a round trip is about 11 milliseconds. So with all these small cells emerging, you can actually deal with the LTE part. Now, if you go, you start to see a clear trend. In fact, people I just picked this up, and there are more. In fact, somebody pointed out, I forget, I don't know if he's here, pointed out there are companies who are starting to build these cloudlets. But you can sort of see different companies starting to talk about this. They're saying, oh, for example, here are all the devices. We're going to put some computing resource here. In fact, they've used the term cloudlets here by in their presentations that they have been making as well. And then what I find even more interesting is that they are building base stations now with computing resources in there too that can be augmented. And then if you look further, you start to see that there's a stack. This is a software stack which is sitting inside a base station. This was unheard of in the past. Base station was just a base station, right? With an RF thing. But they call it LiquidNet, and they're starting to build products that they're trying to sell to the likes of Lucent and Ericsson and all these other people who are doing. Because there's plenty of research that indicates that all this is sort of good stuff. So that sort of brings me to the end, and I'll sort of say the following thing. So today, the world is kind of like this. We've got all these mega data centers. They will exist, but I think many more micro data centers are going to get deployed. Now, from cloud computing, it's a very, very big task. So I don't know how many of you work on big data. So if you do work on big data, or how many of you work on Internet of Things, or you are starting to work on things, what is happening here is, and this will address the other question that I was asked, which is that if you, as a company looks at this resource, so let's do some simple math. Let's say there are 40 servers and there are 1,000 of these. So that's 40,000 servers of yours that are sitting around the world, right? And by the way, a lot of the research that happens here in the cloud is about resource management. It's about making sure that the servers are being utilized as much as possible, so at an 80-90% utilization rate, because the more you use the servers, the more money you're going to recoup. You can't have a server work at 25%. So now if you've got 40,000 servers sitting around, you have to figure out a way to use them all the time, right? Yes, there's one way to use them to sort of serve the client side, but then, if the client side is not enough, you might have to do something like sort of distributed analytics. And so if you take an IoT example where you've got all the sensor data and stuff coming in here, instead of bringing it back to the cloud, you're going to do the analytics right here. So things like MapReduce or things like Hadoop, all these things will have to be rethought, because they were brought in. We built those things with the intention that everything was homogeneous, the network was well known, the servers were well known. Now you've added this sort of a component here of networking, and you want to use these things. And like I said, there are cases where the data, you want to keep the data local. So for example, if you have Netflix is running, and you hit the query saying which of the movies are running, running the most or whatever. Or let's say Skype, take the example of Skype. You want that analytics to run right here in all these MDCs. So we have to rethink all the things about how to do cloud computing and managing. And to answer that question about being expensive, let me answer it the following way. So it's not far-fetched to think of a franchise model in this world. Okay, so imagine company A, Microsoft, Google, whatever, builds these things, and then there's just like the ISPs grew in the internet world. You can imagine ISPs growing and saying, "Hey, I can provide this service." Microsoft, Google will say, "Fine, here's a server rack, here's a bit of software, go, you do it." So the cost, the burden, is not necessarily borne by the head, but by the ISPs, and that's their distinct. That's how they create value for their customers to improve their quantity. So there are those other. That's one way to sort of think about it. I'm not sort of going to go too deep into this, and I think that's what it is. So yeah. So the MDC is classic CDNs with edge computing. Blah blah blah. Mobile computing can help. That's it. That's kind of what I wanted to say. But now you can ask me any question you want. Okay.
I just want to make some comments.
Yes, please.
As you saw, in the 2000s, people tried to get their servers close to the Wall Street firms, right? To save on latency. But what has happened? In fact, it is being regulated out. That means now they are going to prevent people from, because it has to do with neutrality, really, that every player is not getting the same access. Yeah. Right? And I believe the same thing is going to happen over here. So you might have the right to put your micro cloud at this ISP. But if in some sense the ISPs then start demanding different rates from different people wanting to put it there, I believe you're going to run into the same type of problem. So I agree that these solutions are quite, quite natural to try to reduce latency. But I think you're going to run into a lot of legal headaches with time, not in the beginning.
So let me address that a little bit. So your point of network neutrality is actually a good one, because yes, somebody would ask, this actually does impact network neutrality. But let me say, give you two points here. So one is that companies are unnamed companies, but you can guess who, are already starting to build products for the enterprise that do this. So you will buy these Cloudlets or micro DCs for an enterprise, and there's nothing about network neutrality that can stop them from doing that. Okay, so that's one. Then the second is there are companies like, in the public space, companies like Starbucks and Barnes & Noble and all the other things, which also provide things, which can also put these micro DCs in space. And that also does not impact the network neutrality in the way, because it doesn't actually, it's not an ISP deal anymore. It's just that there's a cloud cache there too. So effectively what I'm saying is there are other ways that this may not enter the debate of network neutrality, because it is on the premise by whoever wants to improve performance. But if the ISP starts to provide this as a service, then yeah, that question may come up. But it's not clear to me which way that'll go even now. So there will be pushback on both sides. It's a matter of, like, one might argue that it's a matter of whether you can do certain things or you cannot, right? So if you cannot do, like I've given you example, I give you the gaming example. You can't really do a gaming with cloud offload without having something close by.
But actually POP died because of this. POP died, the idea of POPs in those days died because of regulatory issues, not the technological issues.
Yeah, I think you may be right. I can't really argue that because you have more experience in that. But I can say that there are. This is not a POP, because POP was much more about the ISP. This is much more about the end user benefits, and so that may be the slight difference between the two, maybe.
Yeah, maybe if there's a way that you can argue that the user will be the one deciding what sits close, but it's hard here, because you have a shared.
Yeah, because right now the way the world is evolved is it's very dominated by ISPs, right? I mean, it's just that's when you buy a phone, you have an ISP, but it is true that, for example, when I'm back in my apartment, my phone automatically connects to Wi-Fi and not the ISP, and at that point, if there was a micro DC in that apartment, then what is the ISP going to do? I'll have, and so it's going to put pressure on the ISPs to provide the same level of service. So for example, you can think that LTE went pretty hard on this once Wi-Fi became so successful and showed that they can have these large capacities, so LTE started to do. So I think when you start to put the pressure on them, they will have to provide some level of service like they are starting to do with the base stations, like they are trying to build these products in the base stations. The other thing that is happening with the ISPs is that so they are under constant pressure to improve their stock prices too, right? So let me take the US example, because I'm much more familiar with that there. So in the US, if you sort of think, let me draw this little picture. If you think that, let's make the world very simple, right? Say, let's say here are all the cloud providers, and here, so you have Azure, AWS from Amazon, Google stuff, and then here are, let's say, your customers. I'll just make homes or corporations or whatever. Just customer. These are your pipes. This is your Orange, AT&T, or whoever. So what is happening is that they have to increase their revenues. So now in US they are fairly saturated. I mean, they're 300 million population. A whole number of them already have cell phones. Now they can't increase. So how do they increase their revenues? Well, they can charge more, right? Or they can charge these guys more, right? So or they can have more, get more subscribers. Now, getting more subscribers is hard because they're fairly saturated. So that's why the Internet of Things looks very exciting to them, because it allows them to put more devices on their cell networks. but that's TBD. They can't increase the prices because they're already, at an extent. So how much will I pay? I pay $100 a month. I can't continue paying more. There's no way they can increase that. They look at these guys and say, oh, I can't actually do the cloud thing because there are billions of dollars have already been invested, so they can't really do. So what do? They are under tremendous pressure to increase, right? So that is why what you're seeing is they don't want to be a pipe. They actually want to be a service. And they feel like the way they can't hit it here, they have to hit it here. So that's why this cloudlet thing and all starts to make sense. That's why you start to see in the base station software being developed and being sold and things. Now, how in the end it'll pan out, we don't necessarily know. And these guys are doing the same thing. I mean, the picture I painted to you was sort of saying, hey, this latency is killing us, right? We got to get near these guys. So we got to put pressure and put here things. Now, in 2020, who's going to own what? Or is there going to be some other company that owns what? Can't be predicted. But what I can tell you, what I'm pretty sure about is this is not the world that's going to exist in 2020. It's going to be a very different. Computing will be disaggregated. And then you will have to look at all this thing much more holistically in terms of when you do all the things.
Does Microsoft have a strategy? What's your line? You said you did this because Microsoft needed to get into this market. So I mean, without telling us what it might be, can you say that they're going to move in this market? Are they going to solve the problems between Google and the operators?
Well, I don't know if, again, Microsoft is just a bunch of people trying to make money and trying to do smart things. And so part of my job is to just make sure that there is awareness and there's technology that can fix it. So I can't actually, I'm being very honest by saying, is Microsoft going to do it? Well, as long as I'm there, I'm going to make sure that all the right things tend to happen in this space. But business decisions get made in a very, very strange kind of ways.
You mentioned the end liquid net, and as far as I know, Orange was considering installing things from Nokia, which are transparent caches, transcoded. Yeah. But they stopped. I mean, as far as I know, I'm not working with Orange, but as far as I know, they stopped because YouTube is now encrypted and it's useless.
So
there's conflict of which needs to be solved before.
So that encryption thing is another big thing. I mean, ISPs hate it. If everything's encrypted, they can't do a thing to the packet. They don't know what to do. That's a very, very heavy lever the content providers have. But the thing against encryption is the following, which is that in order to do encryption right, you need a lot more infrastructure, right? So for example, Speedy, I don't know if you follow the IDF thing, where Google's been pushing this thing called Speedy, and Speedy has this notion of TLS, and so this in every packet encrypted. Now, in some sense, for a long time, we've been trying to make the internet more pristine in the sense, trying to sort of say that in order to avoid all these attacks and leaks, if everything was encrypted and end-to-end authenticated, that's good. But every time a packet comes here, you need to have a tremendous amount of infrastructure which authenticates it, make sure it's the right packet before it does that, right? That's a lot of money involved here, everywhere. These guys are fighting it tooth and nail because they're saying if it's encrypted, we can't do anything for you. We can't give you differentiated service. We can't give you any better service, and so that's yet another huge issue which has to play. And so. And if you put these micro DCs here, you can sort of encrypt the traffic between the two, and these guys are done. They're just pure pipes at that point. So there is a battle that is going to happen here. And who's going to win that, we don't know. Network neutrality will be a pretty big story in this.
Google will offer ISPs caches to go down, transparent caches, not transparent caches for their service, for their YouTube.
Google's
solve the encryption, but they're taking over control.
So
it's kind of a fight between who's looking after these micro data centers. Is it going to be the operators, the ISPs, or the content providers?
If you look at, there's a paper from USC last year in IMC, and they talk about the spread of Google caches. And they said that in 1 year, they went to more than 2,000. So the way the Google's going about this is YouTube is their big hammer. Everybody loves YouTube, right? And as I said in the beginning of the talk, I said that if you're a little ISP, then you're paying so much money to the upstream ISP, and I can prevent you, then you're going to say, sure, I'll do this. So once they are in, the biggest, hardest problem for these guys is to actually find space and power here, right? They have to scale. So that's why I was talking about the franchise model. Maybe there's another way to do things. But if you, in order to scale here, you need some people to play ball with you. But Google has a very nice asset called YouTube, which allows them to play ball. Other companies don't necessarily have that kind of an asset, so they have to figure out how to get that asset. That includes other companies here as well as companies here. So that the content is a big thing for everybody. Like who provides the content? And in fact, another trend you might be noticing is you may have picked up, like Netflix, for example, does their own content now, right? They have this movie, what is it called, like Games of Thrones or something. Oh yeah, House of Cards. So don't be surprised. Don't be surprised, and here's from now, I won't be surprised if Google start building content, or Microsoft, or Amazon, because content is king. That's it. That's what people want. So, IT companies suddenly becoming content provider. I mean, I don't know. Could happen.
Yeah, because there's not only YouTube. There's also Vimeo. There's also Dailymotion.
Yeah, Dailymotion is one more big one. Yeah.
Yeah, exactly. So
gaming. Yeah.
Not just put. If Google puts, then other players should come into the game.
Yeah. But I have to tell you again, you guys have it good here, because everything that I see is that these pipes are fairly inexpensive for you, but that's really not the case in the rest of the world. It's really bad. So if at all, I don't want to say anybody's a bad guy here. Everybody's trying to do the best they can, but really they are minting money here.
No, but that's because public infrastructure was set up at the time of Orange and France Telecom, which everybody else is piggybacking on.
Yeah.
Whereas the US, it was killed much earlier.
Yeah, it was. but it's not just the US. Even in, like, you go to Asian countries, this is very expensive, and we are paying like level 3, for example. I mean, so this talk was all dedicated to wireless, but and I also work on like hardcore networking stuff, and I mean, people pay lots of money to companies like level 3 and things like that just for that bandwidth. So for many years, these companies have gotten away with a lot of money, which can easily be commoditized. And so one could argue, if you just take a completely academic view of these things, there is no reason to pay this kind of money that is being paid. So anyway, I think it's an interesting time. All right, yeah.
When you were comparing computing locally in the smartphone or offloading, you were comparing in terms of energy consumption, right?
Yeah.
But I think there are other nice criteria. For example, privacy.
Yeah.
The moment your smartphone becomes a gateway between your intranet of things and the cloud, then you may want to aggregate data or to do some pre-computing before sending the data to the cloud. Right?
Yeah, so that's the IoT case, for example. So in the Internet of, when you have all this sensor, you might want to aggregate that data. And sometimes it's also true that certain things are much more locally relevant than globally. So why even waste bringing all that stuff? So you could. Yeah, definitely do that. In fact, on this sabbatical, I spent 4 weeks in London, and believe it or not, I actually wrote a paper which I thought was kind of a nice. There we looked at the problem of vision. So what we said was that we wanted to build we built a security network which was built on top of Wi-Fi, and the idea there was that we would have cameras which will, so we define this notion of droplets, which will actually do some processing right at the camera, because the bandwidth is so difficult in it's, especially wireless bandwidth. So if you think about like security in a wireline world, you've got put all these cameras, and then it all brings it to this big dashboard, and some human being is looking at it, right? You can't actually do that in wireless space because you just don't have the bandwidth to bring it. So you actually have to do processing right at the edge, and only bring in content which is of interest, which is most important, and potentially only bring it up in a way that indexes stuff there. So. So you're right, I talked about energy saving, but there are example after example where you start to feel like, I really don't need to go to the cloud. Why the heck am I going to the cloud? And so now the big question is, who's going to own the cloudlets?
The way to say it is that the part of the cloud is your smartphone, right? It's not that you're using the smartphone to access the cloud, but the cloud is one,
programmatically you have to think like that too. And for software, people who do software engineering, for them the big challenge is, how do you write these apps in a way that that the high school programmer or people with a PhD can write these programs, and they just figure out where to put the computation amongst the different things. Okay, last question. I'm surprised you're all still here. I thought So that's good. I guess it was okay. Yeah, go ahead.
If we continue with the analogy between the classic CDNs that were there for static content and so on, and the cloudlets, which are more for cloud processing, there is the problem of that we were discussing about the ownership, who owns the CDN or the cloudlets and so on. But maybe there are the other problems that are the mechanisms to request the different client requests to the correct DCs and so on. Yeah, for instance, for the classic CDN, we have the request routing, to directs and the DNS and so on. Do you see the same problems for the cloudlets, or it's?
So I'm not sure I understood. Let me repeat and tell me if I understood this right. Like, actually, I didn't really understand. So tell me what you precisely.
I was trying to think about the analogy between the classic.
CDNs and this thing.
So the classic CDN, when you have mechanisms like request routing to decide where is the content is cached. And, I was wondering if you have.
Sure.
Problems, the same problems with.
Sure, I think. I would imagine that Cloudlets will not come in the same shape and sizes. So they will have, there will be some with more processing power, less processing power, more data, less data. And so as to which one you go to, and which one the client will benefit most from, might become a similar problem that a CDN. Yeah, why not? I mean, this is an extension of CDN. This is an extension. It's just saying that instead of caching, you're actually going to do a lot more computation as well on the edges. So I would imagine that as this starts to take off, people will find better ways to do this and have these problems to deal with as well. I was just sort of painted a higher level picture here, but yeah, I would imagine that's probably true. Okay, thank you very much.